now being recorded.
Okay. Let me get the share screen set up. Okay. Do people see this? It looks weird on my screen, but
yeah, it looks fine.
That's fine. Okay, so let's briefly talk about some course logistics. The first is that we just made a piazza last night, and I think Shahar like auto-enrolled everybody who's registered. Is that right, Shahar?
Yeah, that's correct. But everybody was registered last night, I guess.
But this isn't everybody, so let me also put the link in the chat so you can go register yourself.
It's on the website. I added to the website.
So you put it on the website. Okay, go to the website and you can register through there. We haven't yet set up a grade scope for homework, but this will be forthcoming, and it'll be on the, presumably, I guess, both on the website and Piazza once it is.
I mean, just one thing that we are going to use Piazza for all announcements, not emails. I mean, make sure you register if you want to get any announcements or anything. And also, you know, it's good when they have discussion forums, which is great. I think, I mean, once people have questions, then it's best that you ask there so that other people get to see the answer. And
yeah.
Yeah.
So homework 1 will probably be out by the end of this week, and I guess due in 2 weeks. And it should be, we'll post it on the website and on Piazza, so be on the lookout for that. The third, and all of these things you should be able to see on the website, but I just want to mention them so everybody is on the same page. There are office hour times now. I think, if I recall correctly, Shahar is 10 to 11 on Friday. Is that right?
Yeah, that's right. Yeah.
It's 10 to 11 a.m. on Fridays. And I am 12:30 to 1:30 after class on Tuesdays. Okay, I think that's all of the logistics.
Yeah.
Okay, so let's go ahead and actually get started with class problem.
Wait, maybe one more thing. I mean, as you said about homework. So if you remember, homework can be done individually or in pairs. So if you want to find other students, I mean, so Piazza has this option of finding, you know, team members. So you could use this feature if you're trying to find, you know, somebody to do homework on with.
Yeah, I personally encourage people to do the homeworks in pairs. So hopefully, if you don't know anyone in the class, the Piazza tool is great for finding teammates. Thanks, Sahar. Good reminder. Okay, so I want to start by briefly reviewing some of the definitions we went over last time, just to make sure everybody's on the same page when we go into proving the Cheeger inequality today, which will be the main focus. So let's start by recalling a few definitions from last lecture. So mostly we talked about kind of a number of different definitions for expansion. Today we're going to focus on edge expansion and spectral expansion. So let's review them. So the first thing is edge expansion. So for simplicity, all of today, I'm going to be assuming that whenever I say a graph, I really mean a d-regular graph. I will always be assuming that my graphs are regular and that their regularity parameter is d, that every vertex has d edges. So we call a d-regular graph GVE or an epsilon edge expander if for all subsets of vertices of size at most v over 2, or kind of otherwise you can think about this as for all cuts in the graph. The following holds. The expansion of that set, which I'm going to denote by HS, and is defined to be the number of edges passing between S and V without S that are crossing the cut. So S bar is just notation for V without S. Over kind of the total number of edges, double counting things within edges within S, is at least epsilon. So morally, as a reminder, what is this saying? Well, it's basically saying there are no sparse cuts. Or when you pick a subset of size less than half the graph, many edges will be expanding outside of that subset. So this is morally what an edge expander is. And there's a second definition related to this that I actually don't quite remember if we covered this last time, maybe at the very end. But I also want to tell you what the Cheeger constant is. And this is just kind of for a given graph G, the Cheeger constant is just like the best possible edge expansion parameter, like the largest epsilon such that the graph is an epsilon edge expander. So slightly more formally, the Cheeger constant of a graph, again, I'm assuming, I guess you don't have to assume regular for this, but the Cheeger constant of a graph, GVE, is, we denote it by H of G. And this is just the minimum over, again, all subsets of size and rows to be over 2 of the expansion of that subset. So again, this is just a formal way of saying it's the parameter that kind of tells you what the best possible edge expansion parameter is for the graph. So this is the Cheeger constant, and we're going to be looking today at connections between spectral expanders and the Cheeger constant, or the second eigenvalue of the adjacency matrix and the Cheeger constant. So since we're focusing on that, let me now remind you what spectral expanders are. So a graph GVE is a lambda spectral expander if the second largest, all of the non-trivial eigenvalues, the second largest non-trivial eigenvalue in absolute value is upper bounded by lambda. And I'm talking about the eigenvalues of the normalized adjacency matrix. So remember, kind of, we write the normalized adjacency matrix as AG, and it has eigenvalues going from 1 down to lambda n, which is at most -1. Sorry, at least -1. Okay, so if the maximum second largest eigenvalue in absolute value is upper bounded by lambda, and this parameter on the left we often write as lambda g. This is kind of in correspondence with hg. This is like the best spectral parameter for the graph. Okay, and this is what's called a so I maybe omitted this. This is what is called a two-sided notion of spectral expansion, because we're both kind of considering the potentially negative side of lambda n and the larger side, positive side, lambda 2. So there are also one-sided notions of spectral expansion, and we mentioned this last lecture. There's something called the spectral gap, which is a one-sided notion. And the spectral gap of a graph is just 1 minus lambda 2. And maybe it's a little bit more intuitive to say it's lambda 1 minus lambda 2. But remember that lambda 1 is equal to 1, right? For the normalized adjacency matrix, because the rows and columns sum to 1, we end up getting that the first eigenvalue is 1. And so the spectral gap is 1 minus lambda 2. And the idea here is that basically something is a good one-sided spectral expander if the spectral gap is large, which is equivalent to saying that lambda 2 is small. Okay, and before moving on to the Cheeger inequality, I just want to recall kind of one more thing. So these are the main definitions we care about, and what was kind of the main theorem that we proved last time? It was called the expander mixing lemma. So maybe I should say lemma, expander mixing lemma. And this gives some connection between kind of edge structure and spectral expansion, right? It said something along the lines of, for all subsets, we have that the number of edges running between S and T is about what you would expect in a random deregular graph. Where this kind of difference is bounded by some kind of function of ST and the spectral parameter lambda G, something like this. So this gave some connection between spectral and edge expansion. We're going to be talking about another one today called Cheeger's inequality. And I just want to remember kind of one key idea from proving the expander mixing lemma that's going to be, again, come up. We're going to reuse this same key idea to help prove Cheeger's inequality. So I want to just remind you of kind of what we did. So the key idea in this proof, or one of the key ideas, was to relate this kind of number of edges passing between S and T to write this in terms of the adjacency matrix and the indicator functions of S and T, right? So we said this was equal to this kind of product. And then all we had to do was we expanded this right-hand term in terms of like the orthonormal spectral basis, right? And then we maybe applied Cauchy-Schwarz a few times, and that gave us the expander mixing lemma. But the key here really was kind of finding this relation between the adjacency matrix and the kind of edge parameter, so that we can then use spectral decompositions to find a relation between the spectrum of AG and that parameter. So this is a key idea you're going to see come up again in today's lecture. So I just wanted to highlight it. Oh, there was one other thing I actually wanted to note, which is to say, why is this called the expander mixing lemma? Because we haven't said anything. Mixing is not a term we've talked about so far, so this might be a little bit confusing. Expander here actually refers to basically this edge expansion part. The kind of edges are expanding as much as you would hope. And the mixing term is actually referring to this lambda G. And we'll talk about next lecture why this is. It has to do with how lambda G basically controls how fast the random walk on the corresponding graph kind of converges to become stable, converges to what's called the stationary distribution. If this doesn't mean anything to you at the moment, don't worry about it. We're going to go into depth next lecture. I just kind of wanted to maybe demystify, what is the name of this lemma? I mean, why is it called this? Okay, so this is all the background I wanted to cover. I want to pause briefly, I guess, and ask: are there, we will need these definitions. So are there any questions about just this review before moving on? Okay. Oh, sorry. I hear some sound, but it looks like it's okay. Seems like no questions. Okay, so let's now move on to this time. So this lecture, we'll be proving Cheeger's inequality. So Shachar, I think, maybe stated this at the end of last lecture, but let me state it again. So Cheeger's inequality basically, morally, says that you can approximate the Cheeger constant by the spectral gap. And what do I mean by that? Well, let's again let's GVE be a deregular graph. Then I claim that HG is sandwiched between two functions of the spectral gap. It's upper bounded by the square root of 2 times the spectral gap, and it is lower bounded by the spectral gap divided by 2. Okay, so I guess let me briefly, Shahar actually kind of already mentioned this last lecture, but let me remind you, why is this important? Well, I would say from a mathematical perspective, it's kind of intrinsically interesting. Like, it's not clear that these parameters are related a priori, and to me, just combinatorially, it's fairly interesting that these things are related. But from a computational standpoint, this is also just very useful because h of g we're often interested in, maybe algorithmically, but it's very hard to compute. Whereas the second eigenvalue of a graph is not hard to compute. We can do this efficiently. And so if we want to just get kind of a reasonable approximation of the Cheeger constant, this theorem is basically saying we can get it by computing the second eigenvalue, which is useful. And it's also even useful, I guess, sometimes from a mathematical standpoint, like Shahar mentioned the Paley graphs last lecture, and gave some theorem saying their edge expansion is kind of almost perfect, almost as good as possible. And this is actually proved directly through the Cheeger inequality. This comes from the lower bound in computing lambda 2 for the Paley graphs. Anyway, the point is just that this is a very useful inequality. So let's go ahead and get into the proof. But actually, I say that, but I actually first want to cover some background. So I want to cover some basic linear algebra background, just to make sure everybody's on the same page. You may have seen this sort of thing before in a linear algebra class, but I just want to make sure everybody's can follow. So we're going to talk a little bit about what's called the variational characterization of eigenvalues. We're actually really only going to cover a very special case of this for lambda 2 that we care about. But basically, what I want to talk about is kind of a different way to characterize eigenvalues that is very useful for getting bounds on the values, and you'll see why in just a second. Okay, so I'm going to claim something about the form of lambda 2. So I'm going to claim that lambda 2 is equal to the maximum over functions that are orthogonal to the all ones function of this quotient of the product of the f's. Oh, sorry, this should be the normalized adjacency matrix, normalized by the norm of f. And I'll note that this this quotient inside the maximum, this is called the Rayleigh quotient. And we'll be using it a lot throughout the proof of Cheeger's inequality. Okay, so maybe this is maybe not immediately obvious, but we can, it's actually not too hard to prove. So let's just go ahead and prove this. Okay, so we need to prove two directions, right? First, let's prove that the maximum, let's just say the right-hand side is greater than or equal to lambda 2. So actually, this is kind of the easy direction. Does anyone want to take a stab at why this is true?
Set f to be the eigenvector corresponding to lambda 2 and then compute.
Yeah, exactly. So because we're taking a maximum on the right-hand side, all we have to do to lower bound is to exhibit some function that has the value lambda 2. And as Nick was saying, this is exactly the eigenvector corresponding to lambda 2. So let me just write it out for simplicity. So we just, let's say, say v2 is eigenvector with value lambda 2. We know this exists by definition. So what is v2 ag, sorry, v2 transpose v2 ag v2 over v2 transpose v2? Well, by definition, this is an eigenvector. So this is just v2 transpose v2 lambda 2 over v2 transpose v2. You get the point. This is equal to lambda 2. So clearly the maximum must be at least lambda 2, right? We've exhibited some function where it's equal to lambda 2. So the maximum of our functions has to be at least this large. And I guess I should note the second eigenvector is orthogonal to the first eigenvector, which is the constant function, the all ones function. So this satisfies, this is one of the functions that we are taking our maximum over. Okay, so now what about the other direction? We want to prove that the right-hand side is less than or equal to lambda 2. And to do this, I just want to expand the quotient for a general function f that's orthogonal to 1. So basically what we're going to do is we're going to take a look at this product. Let's just pull out the denominator for now. And remember, so we did basically the same thing last time, where we broke f up into the spectral basis, into the orthonormal eigenbasis, right? So f can be written as the sum of alpha I vi, where v1 through vn is an orthonormal eigenbasis. And v1 notably is the constant function. And for simplicity, I'm just going to denote this, each alpha I vi, I'm just going to denote as fi. Okay, so let's expand f in terms of its eigencomponents. So we end up getting, because they're eigenvectors, we end up getting that this is lambda I fi transpose fi here. And this is a sum from 1 to n. But then f is orthogonal to the all ones vector by assumption. So it has no component. So alpha 1, its component on v1, has to be 0. So really, we're actually just summing from I equals 2 to n of lambda I fi transpose fi. But remember that the lambda I are sorted in decreasing order. So the largest lambda here is lambda 2. So to upper bound this, we can just pull out lambda 2. Right? So this is less than or equal to lambda 2 over f transpose f. And then we have this summation of fi transpose fi. But because this is an orthogonal basis, right, this is just exactly, this right-hand sum is exactly f transpose f. So this is exactly equal to lambda 2. And so this proves the upper bound. So we have that the right-hand side is both upper bounded and lower bounded by lambda 2. So of course it is exactly equal to lambda 2. And kind of for the full, this is just the characterization of the second largest eigenvector or eigenvalue. But in general, kind of the variational characterization I mentioned is just this idea that you look at the space that's orthogonal to all the previous eigenvalues, and you maximize over this quotient and you kind of get the same thing. Here we have that the first eigenvalue or eigenvector has a particularly nice form, right? It's the constant function. So this will be particularly useful for working with this. Okay, so maybe I should tell you kind of why do I care about, we already have ways to look at lambda 2. Why do I care about this specific way? Well, one really nice thing about this is if I want to lower bound lambda 2, notice that all I have to do is exhibit a function that has large Rayleigh quotient, right? Because the right-hand side is this maximum over such functions. So if I can find a function where the quotient is large, this gives me a lower bound on lambda 2. So it's an easy way to kind of get lower bounds on lambda 2. Okay, so that's the main kind of linear algebraic thing I want to talk about before going into the proof of Cheeger. There's one more kind of essentially a notational trick that I want to talk about, which is something called the Laplacian. So the Laplacian of a graph GVE is written as L, and it's just equal to the identity matrix minus the normalized adjacency matrix. So spectrally, right, the identity commutes with everything. So studying L versus studying AG, there's not really much difference formally. Everything I could do by studying AG, I could do by studying L and vice versa. But it'll be convenient to talk about L sometimes instead of the normalized adjacency matrix. So how do we write out the eigenvalues of L? Well, we'll write the eigenvalues of L in increasing order instead of decreasing order like we did for the adjacency matrix, because we're taking 1 minus, we're kind of flipping everything. So we'll write the eigenvalues as mu1 through un, and one can prove they're between 0 and 2, and the first one is equal to 0, which is a useful fact. And notably, right, what's the connection with the adjacency matrix between the lambda I and the mu I? Well, it's not hard to see just directly using this definition that mu I is equal to 1 minus lambda I, and mu2, therefore, is the spectral gap. So it's not hard to kind of imagine that if what we want to talk about is a spectral gap, working with the Laplacian might be the right choice, right? Because if we want to analyze kind of the second smallest eigenvalue of the Laplacian, this is the same thing as analyzing the spectral gap of the adjacency matrix. So maybe kind of this will be the right thing to look at. And it kind of turns out it'll be useful. And let me say maybe one more thing before moving into the proof, which is just kind of what does the variational characterization of mu2 look like versus lambda 2? So just using kind of exactly the same proof in the same ideas, but flipping things because we're taking 1 minus, mu2 will be equal to the minimum over functions orthogonal to the all ones vector of f transpose, now the Laplacian, f over f transpose f. And I forgot to say before, kind of notationally, so this was called the Rayleigh quotient. We're going to denote it by RL of FL, where f and L here, f is an arbitrary function, L could be an arbitrary matrix. In general, we will be working with L being the Laplacian for the rest of this lecture. I think every time it'll be the Laplacian. Just in general, we'll denote this as RL function matrix. And this is just the quotient given on the left. Okay, so similarly, this characterization of mu2 says if we can find a function f with small Rayleigh quotient, then we can upper bound mu2, which is the same as lower bounding lambda 2, right? Because mu is equal to 1 minus lambda. Okay, so that's all the background that we need to go through for the proof of Cheeger's inequality. So again, I want to pause and ask, are there questions on the background here before we actually jump into proving the result?
Yeah. Oh, did somebody else? I had a question on kind of definitionally. Wait, sorry. Alexa, stop. Alexa, stop. I'm so sorry.
It's fine.
So in the definition of the Rayleigh quotient,
yeah,
it talks about like f as an like an arbitrary function, but you use like the eigenvectors later on, right? So I'm a little confused, like why like the eigenvectors are emblematic of like arbitrary functions, I guess.
So we were just using the eigenvectors. So we used the eigenvector in the first part, right, to lower bound so we're taking a maximum over all possible functions.
Mm-hmm.
Okay, think about it this way. The Rayleigh quotient kind of talks about how the matrix scales the function.
Uh-huh.
And eigenvalues kind of exactly are very similar to this, right? Eigenvalues kind of tell you about how things are scaled in different directions.
Right.
And if you want to find like what's the third largest eigenvalue, I'm going to say let's kind of take everything that doesn't get touched by the scaling factors of the first and second eigenvalue. Let's ignore all of these things.
Uh-huh. And
then I'm going to look at kind of how is, what's the largest possible way I can scale something? Well, it's by lambda 3. It's by the third largest eigenvalue because I've set aside lambda 1 and lambda 2. So, it turns out that kind of the eigenvector corresponding to lambda 3 gets the most scaled of anything. And that's why it is the maximum over all possible functions.
Okay. That makes
so
sense.
like the thing that will be scaled the most is the eigenvector, which is why you see the eigenvector pop up, even though the maximum is over all functions, kind of orthogonal to previous things.
Okay. That makes sense.
Okay, great.
Thank you.
Let me just make one quick comment. I mean, just so it's clear, it's clear to everybody. When we say functions and vectors, we mean the same thing, right? So we identify vectors with the functions and identify like the vectors on V, and this is by vertices, is the same as function from the vertices to numbers, right? Same thing.
Mm-hmm, mm-hmm, mm-hmm.
Yeah. Thanks.
Yeah.
Thanks.
That makes sense.
Yeah, I will try to say functions, but I may interchangeably use vector and function by mistake. those are the same thing. Thanks, Shahar. Okay, cool. Any other questions?
Sorry, I wasn't very focused on, when you say, how can you get rid of the first term in your proof?
Oh, you
The second, yeah.
like here?
Yeah, here. Why you can get rid of the first term?
So this is because we're assuming we get to assume that f is orthogonal to 1, to the all ones function, to the constant function, right? Because when we the right hand side here, we're only looking at functions that are orthogonal to the constant function. In particular, this is orthogonal to the first eigenspace.
Oh, I see. Okay.
And so in particular, it has no projection onto the first eigenspace. So alpha 1 is 0. Right, so I'm basically just noting that f1 is 0. That's all I'm doing.
That makes sense. Yeah. Okay. Thank you.
Yeah, no problem.
I had one more question.
Sure.
So you mentioned that computing h of g is usually computationally hard. Can you expand on that a little bit? Like, can you do it better than brute force exponential time, or why do we care about computing that?
I think even approximating it is NP hard. Shahar, do you know, is that right? Like certain good approximations.
Yeah, I think I don't remember the details, but yeah, I think you're right. That sort of, I mean, ideally, what people would like to prove is maybe doing anything better than what you can prove in Cheeger is hard.
Yeah.
I'm not sure if this is known, but some weaker.
I think isn't it like you can't do better with a degree 4 sum of squares? So like there's some various weaker things known, right?
Yeah, I don't remember, but people believe that it should be hard, to do anything better than what you can get using linear algebra. But proving that is a different story.
Yeah, I guess for why would we want to compute the edge expansion? I mean, it's often just useful to know that a graph is an edge expander, right? If you're looking algorithmically, you want to kind of say things are connected and it can be useful, but to actually talk about this, you need a bound on how good of an edge expander it is, right? You can get this by computing the second eigenvalue.
Yeah, I mean, there are also other reasons. I mean, it shouldn't be clear now, but turns out that using spectral expansion to get edge expansion, you can't get quite all the way. I mean, if you have like a D regular graph, I mean, you could hope that small sets have almost all of the edges going out. Like, a set of size S has like D times S, or close to D times S edges going out. And this is actually going to be useful. We're going to see applications in week 3 to a couple of applications where that's going to be crucial, getting very close to maximal edge expansion. But turns out that if you just use spectral techniques, that the best you can hope to get is D over 2. Getting half the edges going out, not all of them. And for many applications, you really want to get like 90% of them going out. And proving that using spectral techniques, I mean, we don't know how to do that. And in fact, it was a breakthrough where people were able to prove or to construct graphs with edge expander close to maximal and prove it without relying on edge expansion. So we might talk about that in week 5 when we talk about the Ziegler product.
All right, let's go ahead and move on to the proof because it's a little bit long. I want to make sure we get to a certain point in the proof today. So we're going to go ahead and start with the lower bound. And let me just restate this. This just said, I think as written, this was the lower bound. But notably, this is equivalent, right? We're going to be talking in terms of Laplacian, so let's rewrite this in terms of mu instead of lambda 2. This is equivalent to proving that mu2 is less than or equal to 2 hg. So we want to upper bound mu2. And remember that when I was talking about kind of the variational characterization, I said exactly the reason that we want to build this is that we can upper bound mu2 by exhibiting a function with small Rayleigh quotient. So this is going to be our strategy. We're going to try to exhibit some sort of function whose Rayleigh quotient is bounded by the right-hand side here.
But maybe let me say one thing that's a bit more high level. So really this direction says the following thing. if a graph has like a really sparse cut, then it's lambda 2 has to be very close to 1, or mu2 has to be very close to 2. It cannot be a good expander, right? So it shows having a sparse cut means you cannot be a good expander. That's going to be the easy direction. The hard direction is going to be the other side, so that if you are a good expander, then somehow you do not have sparse cuts.
Yeah. So this is a good way to talk morally about the Cheeger inequality, and it's also kind of how we will prove it directly. Except we'll be using the Rayleigh quotient to kind of bound to talk about the spectral parameters. Okay, so proof. So we want to find a function f that's orthogonal to the all ones vector, such that the Rayleigh quotient of f with respect to L is less than or equal to hg. So by the variational characterization of eigenvalues, this would be sufficient to prove the lower bound here, to prove the theorem, the Cheeger lower bound. Okay, so what's kind of a natural way to try to approach this? Well, remember that hg here, the Cheeger constant, is a minimum over h of s for all sets s of size less than or equal to v over 2. So let's just recall h of g is defined to be minimum over subsets of size at most v over 2 of h of s. So one natural strategy is let's maybe try to actually find not just one function, but let's define a function for every set s and try to prove that it has, try to find a function that has small Rayleigh quotient. And in particular, let's try to find a function fs for all sets s of size at most v over 2, such that the Rayleigh quotient of fs is less than or equal to 2 times the set specific expansion parameter h of s, which let's just recall that this is defined as the number of edges passing between s and v without s, and over normalized by the total number of edges. Okay, so certainly if we can do this, this is good enough to prove that there exists a function satisfying this upper bound, right? Because hg is a minimum over hs, so there does have to be some set s that realizes this bound. So if we can find, if we can prove this for every set s of size at most v over 2, we'll be done. So this will be our goal now. Okay, and so what's kind of a natural function to try to choose? Well, the first thing that you'd think of would probably be the indicator function for s. We want something that's related to the cut. So let's just say for everything that's in s, let's give it 1. For everything that's outside of s, let's give it 0. But this has an obvious problem, right? This is not orthogonal to 1. So we can't use this, but we can use the next best thing, which is that we can just subtract out the constant part of this function, right? So, okay, it's not orthogonal to 1, but we can let fs be kind of the indicator function for s, and then I'm just going to subtract out the function's expectation so that it is now orthogonal to the all ones vector, right? So just a little bit more explicitly, we have fs of v is equal to 1 minus, so the expectation is s over n. N here is the number of vertices, where v lies in s, and it's minus s over n, where v lies in s bar, if it is outside of s. And so, okay, we're going to show that in fact, this function does work. We will show that the Rayleigh quotient of fs with respect to L is indeed less than or equal to 2hs. And we're just going to do this by direct computation. We're going to compute the numerator and denominator, So we need to compute. So let's start by doing kind of the easier term, which is Fs transpose Fs, so the denominator of the Rayleigh quotient. And this we can just compute directly, right? Because I defined the function for you. So let's just compute it. So Fs transpose Fs, well, we have S terms that has value 1 minus S over n. And then we have n minus S terms, which is also known as the size of S bar, which have value negative S over n, but we're squaring it. So it'll remain positive. Okay, and let's just kind of notationally rewrite this. So let's pull out n squared here. This becomes n minus S squared. And now we see we have a lot of terms that are we can pull out from both sides, right? In particular, we can pull out S n minus S over n squared on both sides, and then we're left with n minus S from the left and S from the right, right? But this just cancels and becomes n, right? So notably, this is equal to S times n minus S over n, and n minus S is just the size of S bar, right? This is the size of everything not in S. So we'll write this as S bar over n. Okay, so that was easy. That was just a direct computation. So let's now do maybe the slightly harder part, which is that we want to bound Fs transpose L Fs. And here, this is the reason why I highlighted the trick we used to prove the expander mixing lemma, because we're going to essentially use it again here in maybe a slightly different form. So let's look at F transpose L Fs. Let's actually expand out Fs. So recall that this is equal to the indicator for S minus, maybe I should write S over n times the all ones vector applied to the Laplacian. This is transpose on both sides. And then the thing to notice here at first is that we can really simplify this, because we know that that the all ones function is in the kernel of L, right? It's an eigenvector with eigenvalue 0. So namely, L1 by symmetry is equal to 1 transpose L is equal to 0. So this basically lets us kill the constant terms. They don't have any effect at all because they're in the kernel of L, right? So this is now equal to just 1s L transpose L1s, which is a much simpler term. It's starting to look like the sort of thing we were dealing with in the expander mixing lemma. So let's now expand out. Let's remember what the Laplacian is. The Laplacian is just 1 minus the adjacency matrix. So this is equal to 1s transpose, expanding this out, 1s minus 1s transpose adjacency matrix 1s. And then, okay, the first term is easy, right? This is just by direct commutation. This is just the size of S. It's 1 when the node is in S, 0 otherwise. So the first term is just equal to S. The second term is exactly what we talked about last time, right? This counts, it's lost the normalization factor of D, but this counts the number of edges that go between S and S, right? So this is exactly ESS over D. So remember last time we had multiplied AG by D. So now we have to divide to get the same thing. And I claim, and I'll justify this in just a second, that this is actually equal to the number of edges going from S to outside of S divided by D. And why is this last thing the case? Well, notice that if we add up kind of all of the edges leaving S, and all of the edges that stay within S, what do we get? We just get the total number of edges, right? Double counting things that are within S, right? And because we're working with a D-regular graph, this is just D times the size of S. And so, dividing by D and subtracting gives that this is exactly this second equality, right? So we get this nice connection between the number of edges going between S and S bar. And so now we can put these together to compute the Rayleigh quotient exactly, right? So we have that the Rayleigh quotient of Fs with L, which remember by definition is this quotient. But we just computed these things. So what is this? This is ES S bar divided by DS S bar N. And notice that here, this is HS, right? This is how we defined HS. So this is equal to HS times N over S bar, which is not quite what we wanted, right? We wanted to upper bound this by 2 times H of S. But remember that we were assuming at the start that the size of S is at most half the graph, is less than or equal to N over 2. So this means that the size of S bar, the size of N minus S, is greater than or equal to N over 2, right? And this means that we can bound this second term by 2. So this is in fact less than or equal to 2HS, which is what we were trying to prove. So for every set S of size less than or equal to V over 2, we've exhibited a function whose Rayleigh quotient is less than or equal to 2HS. And because one of these HS has to realize the Cheeger constant, has to be as small as the Cheeger constant, we've gotten the desired bound, right? So therefore, there must exist F orthogonal, and all of these are orthogonal to 1. So there must exist F orthogonal to 1, such that the Rayleigh quotient of F with L is less than or equal to 2Hg. And by the variational characterization of eigenvalues, this gives that mu2 is less than or equal to 2Hg. So I guess just to circle back on what Shahar said at the beginning, what we're doing is that we're proving if there's kind of a sparse cut, right? If there's some S such that there's not many things crossing between S and S bar, we're finding, this tells us that we can construct a function with small Rayleigh quotient, which implies bounds on mu2 by the variational characterization of eigenvalues. And that proves the lower bound. Okay, so let me pause for questions on the lower bound before we move into the upper bound. Okay, sounds like no questions.
Sorry, I have a question.
Yeah, go ahead.
Does this proof require the graph to be deregular?
That is a good question. I mean, obviously this specific proof does, and there are irregular versions of the Cheeger inequality. Shahar, do you know if you need to change things much for that?
No, I think everything's exactly the same. You just, the way you normalize, you need to work a bit. It's going to be basically, instead of D times S is going to be the type of number of edges live in S. But other than that, everything is exactly the same. I mean, nothing major changes, just you need to normalize with the right thing.
I'm just curious, how about the other side of the bound? So does Cheeger inequality require the graph itself to be deregular?
No, I'm asking, in general, no, there is no reason for the graph to be regular. I mean, as far as I know, both sides work for also non-regular graphs once you define the, HFS the right way.
Yeah, I'm trying to think if anything actually goes wrong on the upper bound. I can't at the moment think. Yeah, you just have to be slightly more careful with how the Laplacian is defined, I think, and like it's a little bit more of a pain. But I think it should still work out.
Yeah, I mean, also the adjacency metrics you want to define in a way that corresponds to the
random walk on the
how's it called,
Okay. Okay.
I mean, the distribution that you get on a random graph. On
The
the graph.
stationary.
Stationary, right? Sorry, I was blacking out.
Yeah, yeah. So morally, these things should be the same, but the definitions are different. It's a little bit more of a pain to write out.
Got it.
Yeah, good question.
Thanks.
Yeah. Also, let me just add that the reason we're looking on regular graphs is because, as we'll see later, in all the constructions you automatically get regular graphs. So there is no strong reason to study non-regular graphs. You can everything generalizes, but you don't need to.
Okay.
When we go to high dimension expanders in the second part of this class, yeah, then we need to consider non-regular graphs as well. But for this first 5 weeks, now we don't have it.
Okay.
Okay, good questions. Let's go ahead and move on because this second part is substantially longer, I'm afraid. So I guess traditionally this direction is considered the hard direction of Cheeger's inequality. Shahar mentioned that the previous direction was called the easy direction. I think this is a little bit of a misnomer. I would call this the long direction, not necessarily the hard direction. The proof is still fairly elementary. It's just it takes a little bit more setup to actually to get there. So we won't actually finish this proof today. We'll probably pick up next time to finish it off, but we'll hopefully get through kind of the first the main portion of it. And okay, so what's kind of morally the idea? And Shahar hinted at this earlier, which is what did we just prove? So for the lower bound, we proved that the existence of a sparse cut implied a function f with small Rayleigh quotient with respect to the Laplacian. Now we're going to prove the converse. Right, so now converse. We'll prove that existence of f with small Rayleigh quotients, this will imply the existence of a sparse cut. And notice this is actually slightly stronger than Cheeger's upper bound. To get Cheeger's upper bound from this, you just do the same trick we did before, where you plug in the eigenvector. So you'll plug in the eigenvector corresponding to mu2, and this will give you a Cheeger's upper bound. I'll write explicitly what I mean by this in a minute. But okay, so I'm claiming that if you give me a function f with small Rayleigh quotient, it implies the existence of a sparse cut. And in fact, the way that we're going to prove this is constructively. We're going to actually build an algorithm that takes in a function with small Rayleigh quotient and outputs a sparse cut. So again, this is even stronger than the existential statement. We'll actually be able to constructively do this relatively efficiently. Okay, how? We will do this through what's called Fiedler's algorithm. And this is actually a very simple algorithm. It has three steps, if you can even call them steps. The hard part, or the long part, is its analysis. So what do we do? Okay, well, step one, which is basically just bookkeeping. Let me maybe first say the input is a function f, and the output is a set s and v, or you can think about it as a cut equivalent. Okay, so it's going to input a function, it's going to output a cut. So what do we do? Well, I said step one is bookkeeping. We're just going to sort the vertices in which way do I want to sort them? In increasing order with respect to f. So we're just going to label v1 through vn such that they're in increasing order like this. So not really even a step, just bookkeeping. Okay, now we'll actually do something. So for all indices between 1 and n, maybe n over 2, we will compute basically how sparse the cut is. We'll compute the expansion parameter for HSI, where what is SI? SI is just the first I vertices that are ordered in this way. So SI is just equal to V1 through VI. So basically, I have these sorted, sorted vertices that I'm just kind of going through, considering every possible break between them, and I'm checking what's the expansion of all of these cuts. And then the third thing, well, we're trying to output the sparsest possible cut, right? So what's the natural thing to do? Well, let's just output the minimum, output SI that minimizes HSI. And by minimizes, I mean over these cuts considered by the algorithm, not necessarily over all possible cuts. So it goes through, it computes, it looks at all of these kind of single breaks on the sorted vertices, and then it just outputs the sparsest one. So this is the algorithm. Very simple. What's kind of the guarantee that this algorithm has that we're going to try to prove? That's a little bit more complicated. I'm going to call it Fiedler's guarantee. And the idea is that if Fiedler is given a function orthogonal to 1, then Fiedler's algorithm will output S such that H of S is less than or equal to 2 times the square root of 2 times the Rayleigh quotient of FL. So this is kind of the bit that maybe shouldn't be intuitive. It's at least a priori. It's not at all clear to me why this would be true, but we'll see why. So the claim essentially is that if F has small Rayleigh quotient, then Fiedler's algorithm will output a sparse cut, where how sparse it is based on the Rayleigh quotient of F. And the proof of this kind of comes in 2 parts, and we're only going to go through 1 part today. So kind of 2 parts. Part 1 is a simplified guarantee. And what do I mean? Well, in Fiedler's guarantee, all that we're assuming about the function that gets passed in is that it's orthogonal to 1. Right? I'm going to put an additional structural constraint on F. I'm going to assume that F is non-negative. This will really help us prove the guarantee statement.
I don't think it's in addition, right? It's instead. When you
What?
can't be in the negative and orthogonal to 1 and not be identically 0.
Right. Sorry. We don't want it to be right. So I'm not assuming it's orthogonal to 1. I will assume instead that it's non-negative. Thank you. So instead of F orthogonal to 1, that is a good point. And then part 2 will basically be reduce the full theorem to part 1. Hopefully in the next 20 minutes, I will prove part 1 to you. Part 2 we'll cover next lecture. So let me actually just say before doing part 1, let me explicitly write out why does this prove the Cheeger upper bound? Well, notably, V2 is a function orthogonal to 1 such that the Rayleigh quotient of V2L is equal to mu2. So if you give Fiedler's algorithm V2, it'll output a cut, right? So if you feed Fiedler's algorithm this, it'll output S such that H of S is less than or equal to the square root of 2 mu2, which is equal to the square root of 2 the spectral gap. Right, so if we can prove this Fiedler guarantee, this is actually directly stronger, right? We'll immediately get Cheeger's upper bound. I guess I can pause quickly to ask if there are questions about the theorem statements here before I prove it. Okay, cool. Let's get into it and attempts to prove this. So the key idea is to use what's called the probabilistic method, or one of the key ideas. And if you haven't heard of it, what is the probabilistic method? Well, usually, at least how I've encountered it, this is basically some method of proving the existence of some sort of object that you care about. So maybe you'd like to prove that some sort of structure appears in a graph. And how might I do this? Well, I'm going to say I'm going to build kind of a distribution over graphs such that I can prove that this object occurs with probability greater than 0, with strictly positive probability. So if I just want to prove that the object exists, this is enough, because if the object doesn't exist, then clearly no matter what distribution I pick, it will never occur. It will always occur with probability 0. So if I can kind of tailor a distribution to this object, if I can find a distribution that has a non-trivial probability of it appearing, clearly I've proved existence of the object, right? And this, this sounds a little bit silly, maybe if you're hearing it for the first time, but it's an extremely powerful tool in combinatorics, and here we'll see it used for an algorithm. And if you haven't seen it before, I highly recommend checking out Alone Spencer. This is a really good combinatorics book on the probabilistic method. Anyway, as an aside. Okay, so let me say, I guess, a little bit more explicitly. How am I going to use the probabilistic method? Well, what I'm going to do is the idea is to find a distribution D over cuts considered by Fiedler's algorithm. Considered by Fiedler, such that the probability over this distribution of cuts that HSI is less than or equal to our desired quantity, 2 times the, 2 should be in the square root, twice the Rayleigh quotient of F with L is strictly positive, right? So if there exists a distribution over the SI such that this occurs with non-zero probability, then of course one of the sets does actually have to satisfy it, right? If none of the sets satisfied this bound, then clearly any distribution I picked, I would get the probability of seeing it was 0. So it's enough to just bound this probability, and this is the probabilistic method. Okay, but dealing with the probability itself directly is a little bit annoying. So I'm actually going to kind of prove an expected version of this statement that implies it. It's just a little bit easier to work with. So I'm going to claim that it's kind of enough to prove this expected version of things. So all the expectations I'm taking here are over this distribution D. So I'm going to prove that kind of, let's take the expectation of SI bar divided by the expectation of D size of SI. So this is basically just some expected version of the size of the cut of the expansion parameter, right, of HSI. And my claim is that if I can prove that this is less than or equal to the square root of 2 times the Rayleigh quotient of FL, that this will actually imply that the probability over D, this will imply the above. So in other words, it's enough. I just claim that it's enough to bound this left-hand term. That'll imply the right-hand term that by the probabilistic method will prove the theorem. Okay, let me actually prove this to you. It's just a little bit of probabilistic manipulation. So, okay, first let's just do some things for notational simplicity. So let's let X be a random variable distributed like D that takes on values ESI, SI bar. So this is basically looking at the numerator. Let's let Y be a random variable taking on dsi. And let's let R be equal to the expectation of X over the expectation of Y. And the first thing to notice here is that by linearity of expectation, the expectation of X minus RY is equal to 0, right? Because I'm just, if you just expand this out, you just get expectation of X minus expectation of X, which is of course 0. And the idea is that this implies that the probability that this event X minus RY being less than or equal to 0 has to be strictly greater than 0. Why? Well, otherwise this variable would be strictly positive, and the expectation of a strictly positive variable can't be 0, right? So this statement implies that we have the probability of X minus RY is less than or equal to 0 is greater than 0. And now why is this useful? Well, the event X minus RY is less than or equal to 0 is equivalent to the event that X, because Y is strictly positive, I can divide by it, that X over Y is less than or equal to R. But what is X over Y? This is just the variable, right? This is just the variable that has value HSI. And what's R? Well, just plugging in the definitions here, right? This is expectation of E SI bar over expectation of DSI, right? So namely, if these two events are equivalent, what do I have? Well, I can trade out the events inside the probability, right? So namely, I have that the probability that X over Y is less than or equal to expectation of E SI bar over expectation D SI is greater than 0. And maybe actually, let me say by assumption. So we're assuming, right, that we're assuming some bound in the beginning on this term, right? So this is less than or equal to 2RL FL is greater than 0. And that's exactly what we wanted to prove, right? We wanted to prove, because this is HSI. So that was exactly the claim, right? That this implied the probability that HSI was less than or equal to the square root of 2 times the Rayleigh quotient was greater than 0. So in other words, all we have to do is analyze these expected probabilities, which is a little bit easier to handle than kind of just directly looking at this distribution. Okay. So now kind of the key step in using the probabilistic method basically is always finding the right distribution. What is kind of the correct distribution to get non-zero probability, or in this case, to bound the expectations by what we want. And so, okay, I'm gonna describe the distribution for you, and it might not totally make sense at the moment, but we'll see why it's natural later on in the proof, and I'll try to give some intuition for why it is. So we'll pick the distribution D in kind of 2 steps, or rather, let's describe D in 2 steps. In step 1, we will pick a parameter T between 0 and 1, such that not T, but T squared is uniformly distributed on 0, 1. And I'll say why kind of we pick T squared instead of T in just a second. And then 2, we will output, we have to have, there's a distribution over cuts considered by Fiedler, not over numbers 0 through 1. So what am I using this for? We'll output the cut ST, which is defined to be all nodes such that f of v is, is it less than or equal to or greater than or equal to? Sorry, I'm forgetting this. I think we want it to be greater than or equal to t. Okay, so what's the intuition behind this? Well, let me just mention the intuition behind picking t squared to be uniformly distributed throughout 0, 1. And the idea is that we're kind of, in the end, right, we want to end up kind of massaging things into the form of the Rayleigh quotient. And the Rayleigh quotient is basically a statement about squares, right? The bottom is this sum of squares over the value of f. And the top is some kind, if you work it out, because the Laplacian is 1 minus the adjacency matrix, this is some sum of kind of squared difference of values on nodes corresponding to edges in the graph. And the intuition is just kind of, you want to be able to massage things to be in terms of squares. And this is why this t squared term comes up instead of t. And we'll see in the computation, exactly what I'm talking about. I should probably also mention, we will assume that the largest value of f is equal to 1. And this is just so that you can kind of end up getting any cut from the 0, 1. This is basically just like simplifying notational assumption. And we can do this because scaling f doesn't change the Rayleigh quotient at all. And f is non-negative, so it doesn't change any ordering. So scaling by a positive constant essentially changes nothing. Okay, so let's now actually analyze the two terms. Hopefully I can do this in time. So the first thing we want to analyze, right, is the expectation. So I'm going to move from, so before I was kind of saying SI, and these were the cuts considered by Fiedler's algorithm of V1 through VI, but it's equivalent to talk about ST, where the cuts are defined in this manner, just because each of these is actually associated to one of the SI cuts, right? Because the SI cuts are just a cut in the sorted order of V1 through Vn. If I take everything that's greater than or equal to t, this will correspond to one of the SI cuts considered by Fiedler. So taking the expectation over ST is the same as taking the expectation over SI. It's just a little bit more convenient for the computation. Okay, so I want to analyze this term. And the idea is to use a very basic trick for analyzing expectation. We'll express the size of ST as a sum of indicator functions, and then we'll use linearity of expectation to analyze this. So right, in particular, I claim that this is equivalent to d times kind of the sum of the expectation of some, this is the sum over vertices, of some expectation of a variable where this is kind of the indicator that V lies in ST, right? So what is the size of ST? Well, this is just the sum of, the indicators of whether V lies in ST or not. So we can split it up as the sum of this indicator and use linearity of expectation. Okay, and now we can, now it's an indicator, we can easily compute the expectation. What's the expectation that V lies in ST? It's just the probability that V occurs in ST, right, kind of by definition. So this is equal to the sum over the probability that V lies in ST. And now we can just directly appeal to how we defined our distribution, right? So this is equal to D times the sum over V and V of the probability that T is less than or equal to FV. This is just how we defined the cuts. And then the thing to notice is that because F is non-negative, we can trade out the event T is less than or equal to FV with T squared is less than or equal to F of V squared. But remember that T squared is uniformly distributed. So what's the probability? We have this graph here, here's F of V squared. What's the probability that T lies in this portion? Well, it's exactly F of V squared because it's distributed normally, right? So this is equal to D sum of V of F of V squared. And this can be rewritten as D F transpose F, right? So, okay, we're already seeing that we're in pretty good shape because we're getting this, this is the denominator. We're seeing this F transpose F is showing up. I'm wondering if I should wait on the analysis of the numerator until next time. Shahar, do you think I should?
Yeah, I think probably it's a good idea.
To wait on. Okay, so the analysis of the numerator is slightly more complicated. So I want to have a little bit more than 3 minutes. So let me just stop now for questions about this part of the analysis or anything about Fiedler's algorithm, and then we'll finish the proof by bounding the numerator next week, and then show the reduction to the case that f is non-negative. Okay, let's open things up for questions.
So generally, we're picking a distribution here that sort of Max wants to pick values where f is large.
Yeah, it will bias things more towards that.
Okay.
There's also like a minor technical point here, which is, at the very end, you want to cut S size as most V over 2. But I think that this first step doesn't actually guarantee that. You get some S, some size, and only when we reduce to this non-negative case, we can actually guarantee that size of S is most V over 2. Because here, think about it, it's using T uniformly between 0 and 1, or not T squared.
Yeah.
You don't really have a guarantee on the size of the cut. That's a minor point.
I thought that the way that it actually ends up working out, like you get the result, like it shouldn't matter, right? Because
but the normalization matters, right?
Like but I think if you in the end, like the way they do the normalization in like the Trevisan proof is by min S of V and V minus S. So I think in the end actually you do, like it doesn't end up mattering in set point. Maybe I'm wrong though.
Okay, could be.
But I actually checked this last night because I had the same concern, and I thought it didn't end up mattering. But I'll double check again before next lecture.
All right.
Yeah, in the second part though, you do need to prove, like there is something about proving that the reduction stays at size less than V over 2, because that is important. So this does come up at some point. I'm just not sure this is the point in which it comes up.
Yeah, let me just say one thing about why this V over 2 is important. I mean, let's say you want to get a sparse cut, and you say, well, let's take, all the nodes except one, but only a few edges going out. So it's true, but somehow it's meaningless. But it's such a big set that you don't have any space to go out to. So really to say you have a sparse cut, you have a small set. It has potentially many new nodes to go to, many edges to have, but it doesn't have.
Right, so this is why I initially defined it to only consider kind of the cuts over the first and over 2. But you can also define HSI to be normalized by the minimum of the size of SI and the size of V without SI. So you always want to take things corresponding to the smaller set for the reason that Shahar was saying.
Sorry, I mean, right now, like the way you have defined the distribution, I mean, wouldn't it be like easy to just define it like you pick a vertex with probability like f of v squared? Is it going to be useful in the later step or? Like right now,
okay. This is going to let us express things in terms of the Laplacian.
I see.
But it's not independent, right? It's still the marginal distribution of independence, right?
Yeah, so you can choose each vertex independently with probability f of v squared, right?
But that's very different. That's a very different process. This is not what we're doing here. So they are not independent, right? So you choose a boundary.
Oh, I see. Yeah, I see.
Yeah, we're gonna need basically with the Laplacian that you want to pick. We're going to need to bound T between f of u squared and f of v squared, where there's an edge between u and v, and we're going to want it to be kind of the difference of the squares to look like the Laplacian. And this is essentially the reason that we like it. It's nice to have it uniformly distributed on T squared.
I see.
But also there using the fact that you're choosing the choice for f of v, if it's in the cut or not, is not independent. It's very dependent.
Yeah, I see. That can be important. Yeah.
Okay, so maybe we should wrap up for today, and we'll maybe recap some of the proof and finish it on Tuesday.
That sounds good. Just one reminder about logistics. Please, everybody, if you're not on Piazza, sign up to Piazza because we're going to put all the announcements homework, anything else on Piazza. Please enough.
Will the homeworks be posted on Piazza or the webpage?
The web page.
I'll post them on Piazza as well.
But
So
Piazza,
both,
wherever you want.
probably. Okay. Thanks, everyone. I guess we will
Is that right?
Thank you.
end.
Stop the recording.